All right, let's go ahead and get started. I want to welcome you to Unit 8. This is the mole, and we're going to be taking a look at the quantitative aspects of chemistry now. And when we say a mole, by the way, we're not talking about this fuzzy creature that you see here, but rather we're talking about a quantity. We're talking about a number of something. So in the same way that a pair of something is two things or a dozen is 12, a mole is this number. It's 6.02 times 10 to the 23rd. Now that's an awfully big number. In fact, it's almost inconceivable how big that number is. It's 6.02 and then 23 zeros, right? But nonetheless, it is the number that is a mole. Now we often say that Avogadro's number is this number of particles, 6.02 times 10 to the 23rd particles. And it's not that I'm trying to be vague by not using the word atoms. It's just that in the same way that when we talk about a pair being two things, they don't have to be shoes necessarily. If I say a dozen of something, they don't have to be donuts, right? They can be anything you want them to be. So in the same way, a mole of something doesn't necessarily have to be atoms, although it's kind of ridiculous to think of it in terms of anything else. For example, because it's such a big number. So for example, if you had a mole of bananas or a mole of tennis rackets or a mole of elephants, well, gee, that would fill up the surface of the earth many times over. They don't exist, right? There's not that many. So there's no point in talking about a mole of tennis rackets or bananas or elephants. We're usually going to be talking about atoms. Folks, I'd like you to do me a favor and go back and look at your notes on scientific notation from the first semester. We're going to be working a lot with scientific notation. You're going to need to be able to use that readily. The other thing is you're going to need to be able to enter numbers into the scientific notation function of your calculator easily. If you don't know how to do that or you need some help, come see me and I'll be more than happy to pass that along. So a lot of our work with moles will involve conversions. To determine the number of grams which 1 mole of a specific element weighs, we'll need a periodic table. So make sure you have that on hand for the remainder of this unit. In each square of the periodic table, the average atomic mass shown tells us how much one atom of that element weighs in an atomic mass unit, or AMU. So if I have one atom, then we measure it in a unit called the atomic mass unit, right? Why? Well, the reason is because of the fact that if we just have one atom, it's ridiculous to think of it in terms of a kilogram or even a gram because they're so small. But if we have a molar mass, if we talk about the molar mass of an element, it has the same value, and it tells us how much 1 mole of that element weighs, right? So let's take a look at an example. I want to take a look at this little section of the periodic table. So we have copper, right? Copper 29 in this case, and the copper 29 has this, and it shows this number, 63.546 in that little box. What does that number mean? Well, what it means is that that's the number of atomic mass units that one atom of copper weighs. Or you could look at it another way. You could say, well, that's the number of grams that 1 mole of those atoms weigh. Now notice that copper is different than platinum or different than silver or different than mercury because, well, that makes sense. 1 dozen donuts is going to weigh differently than 1 dozen bowling balls or bananas or tennis rackets or anything else, right? So the molecular weight is going to be related to this number, right? So if you have 1 mole, it's atomic mass units. If you have one atom, it's atomic mass units, but if you have 1 mole, it's going to be in grams, just like that. Okay, good. Now, 1 carbon atom has a mass of 12.01 AMU. 1 oxygen atom has a mass of 15.99 atomic mass units. So now that we know how to use the periodic table to determine the mass in grams of any 1 mole of any element, we can do mole conversions, right? This is something called dimensional analysis. Dimensional analysis. And here's how it works. Let's take this example. How many grams does 2.50 moles of carbon weigh? How many grams does 2.50 moles of carbon weigh? So I like to do this. I like to circle what I've been given and underline what I don't know, what I'm looking for, in other words. So I start with 2.50 moles of carbon and I put that over 1 times Now what I'm going to do is this. Whatever unit's on the upper left goes in the lower right. Just the unit, not the number. Okay, just the unit, not the number. So moles of carbon on upper left, moles of carbon on lower right. On upper right, we're going to put what we're looking for, the unit we're looking for. I'm looking for grams of carbon. So now I'm going to use my periodic table to determine how many grams that 1 mole of carbon weighs. So look at the periodic table, find carbon, and what does it say? Well, depending on the periodic table that you're looking at, there's different amounts of precision. Mine says 12.01. So I put 12.01 right there. Now what I'm going to do is I'm going to multiply these two numbers. The reason I'm multiplying these two numbers is because of the fact that they're both on the top. And when I do that, and by the way, make sure you're doing this along with me and not just copying, 2.50, get a calculator and do this with me, times 12.01, and here's what I get. I get 30.025. I'm going to write that number right here, 30.025. So if that's the case, why did I write 30.0? Well, let's talk a little bit about significant digits. How many significant digits does a 2.50 have? Well, the 0 counts because trailing zeros count if there's a decimal, right? 2.50. 12.01 has 4. So I'm going to take the less of these two because I'm multiplying them. I can only have 3 significant digits in my answer. So my question will be to you, does the 2 kick that 0 up and make this a 30.1? No, it's not 5 or bigger, and so it does not kick it up. It does not make it bigger, right? So I'm just going to report as my answer 30.0 grams of carbon, and that'll do it for that first one. Let's look at another example. This time we've got 242.1 grams of oxygen is how many moles of oxygen atoms, right? How many moles of oxygen atoms? I'm going to circle what I know and underline what I'm looking for. So I start with 242.1 grams of oxygen, right? Over 1 times 1 mole of oxygen per 15.99 grams of oxygen. Where did I get that 15.99? I got it from the periodic table, right? So whatever unit's in the upper left is going to go in the lower right. Why? Well, so I can cancel them. That's what I'm trying to do. I'm trying to get rid of grams and go to moles. So 1 mole of oxygen weighs 15.99 grams, right? Now am I going to multiply these two numbers or am I going to divide them? One's on top, one's on bottom. So we have 242.1 divided by 15.99. Here's what I get. Well, listen, on my calculator, I get 15.14071295. I can't take all those numbers. I can only take 4 of those numbers. So my 15.1407, the 0 doesn't kick the 4 up, so I'm just going to report 15.14. Don't forget the units, moles of oxygen. 15.14 moles of oxygen, and that's my final answer. Okay? All right, let's move on. Now, let's take our knowledge of Avogadro's number to convert from moles to particles. From moles to particles. It says a sample of boron weighs 22.41 grams. How many boron atoms or particles does this represent? How many boron atoms does this represent? Let's start with what we know. We've got 22.4 grams. We're looking for atoms. Now, remember, though, that in order to go from grams to atoms, we don't have a direct relationship. So we're going to have to go through moles. Let's take a look at how this works. We've got 22.41 grams, right, over 1. 22.41 grams over 1. Always put it over 1 to hold that place. Times, we're going to convert to moles. I can't go directly from grams to atoms, but I can go to moles. So grams and grams are going to cancel away, and I'm left with moles of boron. Now, how do I determine the number of moles of boron per gram? What I'm going to do is I'm going to look at the periodic table, and when I do that, I see that 1 mole of boron atoms weighs 10.81 grams. Now, depending on the periodic table you have, again, it may say 10.812. Whatever your periodic table says, that's what you are going to write. So mine says 10.81. I'm going to stick with the 10.81. So now we've got moles of boron, but is that what I was being asked? No, I'm looking for the number of atoms. So I have another step. This is a 3-step process, right? All right, so actually a two-step process, one step here and one step here. So we have times whatever unit's on upper left goes on the lower right. Upper left, lower right. Then we have boron atoms right there, right? Boron atoms right there. So it's 6.02 times 10 to the 23rd boron atoms per mole. All right, so now what I'm going to do is I'm going to cancel this unit with this unit. The only thing that's left is boron atoms, and that's what I'm looking for. So now what I'm going to do is I'm going to get my calculator. I'm going to multiply 22.41, okay, times 6.02 second EE23 equals divided by 10.81. And what I get is this number, 1.2, actually this is on my calculator, I get 1.247994445 times 10 to the 24th. But I want to round to how many significant digits? Well, how many significant digits are in the 22.41? 4. How many in the 10.81? 4. The 0 counts. 4. But how many in the 6.02 times 10 to the 23rd? The 23rd part doesn't matter. I've got 3. So I can only have 3 significant digits. All right, so in my, again, what I got on my calculator is this right here, 1.2479, like this. Does this 7 kick this 4 up? Well, yeah, it does. So it's going to be 1.25 times 10 to the 24th boron atoms, all right, boron atoms. So now let's try another example. Hope that makes sense. 23.02 times 10 to the 15 sodium atoms weighs how many grams? 23.02 times 10 to the 15 sodium atoms weighs how many grams? So here's what we're going to do. We're going to start with what we know. That many sodium atoms weighs how many grams? So we've got 23.02 times 10 to the 15th over 1. Sodium atoms is on top. That's the unit on top. Times, now what we want to do is put whatever unit's on top, upper left goes on the lower right. So we've got now sodium atoms here, sodium atoms here. They're going to cancel away. And I need to go to moles because I can't go from atoms to grams. So now what I'm going to do is I'm going to say 1 mole is the equivalent of 6.02 times 10 to the 23rd sodium atoms, right? So now what I'm going to do is times so many grams per mole. Moles on upper left, moles on lower right. Those are going to cancel away, and I'm going to be left with grams of sodium. That's what I'm looking for. That's what I want, right? All right, so now what I'm going to do is I'm going to multiply the numbers on top, and I'm going to divide by the 6.02 times 10 to the 23rd. You do this with me, and if you don't know how to enter this into the calculator, the scientific notation into the calculator, you need to either ask me or ask someone who knows, and make sure you can do that. All right, so times 10 to the 15th, and then we're going to multiply that by 22.99. We'll then divide that by 6.02 second EE23. And here's what I get. Let me put that in scientific notation. I get this number, 8.79119269, blah, 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 times 10 to the negative 7. But I can only have 3 significant digits because of that 6.02. So I'm going to round my number to 8.79 times 10 to the minus 7th grams of sodium. Okay? All right. So I think this is a good place to stop. We'll pick it up on the next one with something a little bit more complex, and we'll take it from there. Thanks. I'll see you in the next one.